So hey guys, in this video we are going to solve AtCoder DP contest and we are going to solve all the problems one by one. There are total 26 problems from A to Z in increasing order of difficulty. In today's video we are going to pick problem A, that is frog 1. Let's read the problem statement. What does it say? There are n stones numbered 1 to n. For each I, the height of the stone I is hi. There is a frog who is initially on stone 1. He will repeat the following action some number of times to reach stone n. If the frog is currently on stone I, jump to stone I plus 1 or stone I plus 2. Here a cost of absolute of the height difference is incurred, okay, where j is the stone to land on, okay. Find the minimum possible total cost incurred before the frog reaches stone n. So in this problem we can see that there are total n number of stones. The height of each stone is given and we have to print the minimum cost that we can incur given that we start from stone 1 and reach to stone n, okay. And the steps allowed are that the frog can jump from ith index to I plus 1th index or ith index to I plus 2th index, and each jump costs a value of the difference of the height. There are some sample inputs, okay. So we are given 4 stones with height of 10, 30, 40 and 20. We are at the first stone and we have to reach to the fourth stone. And the solution for this could be like there are many ways. One can be jumping one by one, jumping two, then a one, or like jumping here one, then two, and so on. And in the solution provided, we have the optimal way to do this is going from first stone to second stone and then second stone to the fourth stone, making a jump of 2. Here the difference of the height, the absolute difference is 20, and here the difference between the height, that is 30 minus 20, is 10. So total cost would be 30, and that's the minimum that we can make. In all the other possible paths, the answer would be maximum, more than 30. Okay. So let's try to break the problem into smaller pieces so that we can construct a working solution for this. Let's assume that we only have one stone. We are standing at that stone. Let's say the height of this stone is, let's say A. So what would be the answer at this? Like we are here and we want to reach here. We are already here. So whatever the height, it doesn't matter. We are already at our destination. So here our answer would be 0 if we only have one stone. So let's say we had another stone B with a height of B. So we are standing here and we want to reach here. What we can do, we can make a jump of 1 and simply reach to our final destination. And the cost to do that would be simply B minus A. So if we are at this index and we want to reach at the nth index, then a solution would be just a B minus A absolute difference. Okay. Let's say we had one more stone, a stone with a height of C, and we want to reach from here. We want to reach our final destination here. Now, since a frog can make a jump of 1 and a jump of 2, now here we can see a dilemma of multiple paths existing. We can either choose this path or we can directly make a jump of 2 and reach at A. Let's see what would be the cost of each path. The green path would be like the difference between the height of the stones, that would be C minus B. And after doing C minus B, we would be at stone with the height of B. But is this our final destination where we wanted to reach? No, we wanted to reach at the nth zone. But we can observe that B reaching from B to A already exists. We have already calculated that here. So can't we just use that value? So we can just add the value we have already calculated for B. And let's say we didn't wanted to choose the green path, we wanted to choose the blue path. It might be the optimal one to give us a more minimum value. What we can do is we can simply get the difference, absolute difference of the height of C minus A. Then we can just add the already computed value for the index. Now, what to choose? This or this? And how can we decide that? We can simply decide that with a min function. We can just take the minimum of these two values. And that minimum would be our answer to reach from here to here. So let's expand this. Let's say we calculated for C and there was one more index, let's say D. And now we wanted to reach from this index, that is index 1, to index 4, and we have index 2 and 3 here. Now we can see that there are a lot more options of multiple paths. At index 2 we only had two paths to calculate the minimum from, but now we have paths like jumping one by one, making a double jump, then a single jump, or by making a single jump, then a double jump. So we can't just calculate each and every possible path and try to get the minimum of all those and store for D. That would be an inefficient solution. That would increase our time complexity and give us a time limit exceed. And no one wants that. What we can do is we can see some pre-computations done. We can see that we can make a jump of only 1 and a jump of only 2, and those jump would be made on the indices that are already computed. So we can see that we made a jump of 1, we landed at 2, and whose values are already computed here. We made a jump of 2, we landed at index 3, and whose values are already computed here. So for D also, we can do the same we did for C. We can choose a minimum of D minus C plus answer of index 2 where the C was. Or we can make a jump of 2, we can get D minus B plus answer of index 3 that is already computed. These things are already computed and we get the absolute values here. So observing this pattern, we can make a transition for each ith index. And that transition would be, let's say I am at ith index. I can make two choice, going to I plus 1 or going to I plus 2. And our answer can be calculated as the difference of height between I to I minus 1, I plus 1 plus already calculated value of I plus 1 already calculated. Or if we try to go from I to I plus 2 index, the height difference would be h of I minus h of I plus 2 plus already calculated value of I plus 2. So these things are already calculated and these will be calculated at each and transition. Yeah, let's try to code a solution for this. We have an input format of array n with each index indicating the height. Let's take our input. Okay, we have got our input, and let's try to first write a recursive solution. Let's say the recursive solution already exists and it's a recursion REC, and we are currently at the 0th index. So what would be our answer? Let's say we have our answer equals to recursion of, I'll call the recursion at 0th index, and I'll say that, hey, you are at 0th index and I am giving you my array. Calculate the minimum possible cost to reach from 0th index to nth index and give me that. This recursion will return our answer and we will simply print that answer. So let's take the parameters for recursion. That would be our IDX initialized with 0, and we have our array. Okay. Now we'll make the transition as shown in the image in the right. So at each IDX we can make two choices, two moves. The first choice that we can make is to make a jump of 1. So making a jump of 1, what would it cost? It would cost the absolute difference of our current height, that is r of I minus r of I plus 1th index, plus, and as we assume that our I plus 1 would already be calculated, let recursion handle that. I'll say recursion, hey, give me the value of idx plus 1, and we'll pass the array here. That would be the solution if we make a jump of 1. Let's say we make a jump of 2. Our second solution then would be abs of r of I minus r of I plus 2. We made a jump of 2. And I'll ask recursion, hey recursion, give me the solution of idx plus 2, which is already calculated. And after getting both the solution, that is first and second, what should we return? Since we want to minimize our answer, we'll tell recursion, hey recursion, just return the minimum value of first and second. So now, will this solution work? Absolutely not. This will go on infinitely because we haven't written any base condition. Let's try to think of the base condition. What could be the base condition? Let's say our IDX moved at the end of the array. If our index moved to the end of the array, here we can see that we already did that. We are already at the end of the array, and what we got? We got 0. We are already present at the destination we were at. So if we are at the end of the array, we will just return, hey, I'm already at I'm at my destination, just return 0. Okay, that would be our base case. So now, will this solution work? The answer is no. The solution won't work because we still have some edge cases that may give us a wrong that may give us some errors in the code, and that would be because we are accessing some index without checking whether those indexes exist or not. We are at ith index and we are checking for I plus 1th index and I plus 2th index without checking whether those indexes exist or not. Let's check them whether those indexes exist, then make our computation. And to check, I'll just question here, is my I plus 1th index exist? And to check if I plus 1th index exists, I'll just check whether it's lower than the size of the array. So if this value holds true, my computation would be made. Otherwise, what should I give? Should I give 0 or should I give a very large value? The answer is we will give a very large value because that index does not exist, and we will treat that index as an invalid case, and for invalid case we'll just return a maximum value since when we want to minimize our answer. Similarly, this can be done for the second as well. We will just question, does I plus 2th indexes exist, and we'll check it whether it is lower than r dot size. If it is, the value is computed, otherwise we'll just return int underscore max. That would be a by default maximum value for invalid indexes. I think this solution looks fine to me. We can try to run this. Let's run this. Okay, we got some error that I does not exist. I, and that's valid because we took idx as our variable. Let's do the changes. Okay, so we got a very large value and our solution didn't compute correctly. Checking, let's find the bug in our solution if we are able to find it or not. Oh, okay. Our base condition is actually wrong. We can see that we made a base condition where if we add our final index, we should get return 0. But we are not checking at our final index. Our final index would be add dot size minus 1. So yeah, let's try to run this. And we got a solution 30. Yeah, let's try for one more case. 40, and it's expected. Okay, let's try to submit this solution and let's get a time limit exceed to check whether our recursive solution is correct or not. And yeah, we got a time limit exceed. In this recursive solution, we didn't store any pre-computed values. We are again and again computing all the results. And in the solution, we assume that these values are already calculated. But in our solution, that's not the case. We are uh, just making the recursion call and we are not storing those already computed values. Let's see how we can do that. So the state for our DP would be the index IDX. As for each index, if we have already calculated the minimum value for it, we won't recalculate it. So let's make a DP of int and let's say it and initialize it with -1, saying that it does not exist, we haven't calculated it yet, and pass it with our parameters, vector of int and dp, and let's include that in our recursive call as well. Now we want to return the already calculated minimum value for each index if it's calculated. So we'll make a check. If dp of idx is already calculated, that is to to be already calculated, it should not be equal to -1 that we initialize it with. So if it's already calculated, we'll just return dp of idx. And does this work? No, absolutely not, because we have not saved the values that we are returning in our dp. We'll just make a dp of idx equals to our minimum of first and second. Let's see if this works. Control. Yeah, we got the correct answer. So let's try to submit our memoized solution. Okay, submit. And yeah, it got accepted. So this was one way of coding this problem recursively and then memoizing it. But is there any disadvantage of this approach? And yes, there is a disadvantage that a recursive solution uses stack spaces, and that's not good. And whenever we can convert a recursive solution in an iterative solution, that's considered a better approach. Let's see how we can do that. So we already have the transition for each index. That is, we can transition from ith index to I plus 1th and I plus 2th index. So let's try what our DP would look like. Let's say we have this heights array. We start from height 1 and end at height n, and we want this is our starting index and this would be our ending index, and this would be our ending index. So for each ith index we have already calculated this and this I plus 1th, this is I plus 1, and this is I plus 2. These are already calculated. So for each I we can make a decision of uh, getting the height difference of the heights at the indices and choosing the minimum of both those calculated values. So yeah, that would be our DP. Since we are assuming that I plus 1 and I plus 2 are already calculated, let's iterate backward. We start from I equals to n minus 1, I is greater than equals to 0, I minus minus, and we say our first would be like our recursive solution. Here the first would be the difference between the array I minus array of I plus 1, and what would be added here? Last time we made a recursive call. Now instead of recursive call we will just use the already calculated value. That would just be the dp of I plus 1, and for similarly for second it would be absolute difference of array of I minus array of I plus 2 plus dp of I plus 2. And what would be dp of I? It would be just minimum of first and second. And before we make a final submission, we would need to handle the edges here also. We can just copy this to make that 2, to make sure I plus 1 exists and I plus 2 exists here, and if not we will just store a dummy maximum value that would be int max. And what would be our answer now? Previously it was a recursion of calling at 0th index. Now it would be simply dp of 0th index. Let's see if our solution runs. Okay, so we made a small mistake of index here. Okay, it should be a int I, and we got a wrong answer. Let's try to debug this. Okay, so we can see that we gave 0 as our base case for the last index. We didn't give it here, so we'll need to give it dp of n minus 1 equals to 0 as our base case, and we'll need to start from the second last index to compute. Let's run this, and yeah, we are getting 40. We can just simply paste this iterative solution, copy the problem, and paste it here. We can just comment the recursive solution, we don't need that, and submit it. And yeah, it got accepted. We'll continue with other problems of this education DP contest, and thanks for watching.